Hello everyone and welcome back. In this lecture we'll look at a multi-layer perceptron with more hidden layers. In the previous lecture we looked at a simple model where we had an input layer and an output layer, and we considered these parameters for batch size, number of epochs, and number of classes, and we came up with an accuracy of about 94%. As an exercise for you, you can increase this number of epochs to, let's say, 5 or 10, and you can also increase or decrease the batch size and see the result that you get. What we'll do in this lecture is add some more layers, some more hidden layers, and we'll use the same data that we used in our previous lecture. Okay, we'll start by importing the libraries that we need. I copied this from our previous lecture, so let me run the cell, and then we have our MNIST dataset paths, our X-train, Y-train, X-test, and Y-test. We have seen this before. We took our entire dataset and considered the digit 7, and we selected all the values where the number is 7. We had about 6,200 of those, and we randomly selected 6,300 non-7 numbers, and we combine those to make our training dataset so that we can use them to train our model. Okay, so you have seen this before. I just put everything in a single cell, so I'll run it now. Okay, now back to our lecture. What we'll do for our multi-layer perceptron is change the batch size to 256 and the number of epochs to 10. We'll use the same sigmoid activation, and these are all copied from our previous lecture. So I'm changing the few of the parameters. As usual, we start by instantiating our sequential model, and once we instantiate our model, we add a dense layer. Here our dense layer has 512 neurons and the input shape is 784, and then we add an activation unit of sigmoid. So this is our input layer or input, and this is our output layer, right? Output layer. What we'll do for this lecture is add some more hidden layers. Okay, so let's add a couple of hidden layers. I'll call the first one first hidden layer. So first hidden layer. So for adding one or more hidden layers, we follow the same process. We start out by adding a dense layer, and then we'll add an activation unit of sigmoid. Let's do that. So model.add, we add our dense layer and then specify the number of neurons, let's say 512, and then we add our activation unit, which is sigmoid. Model.add and then activation and pass sigmoid. So for this first hidden layer, it will take the output of your previous layer, which in this case is this, our input. So the output of this input will be taken as an input by this first hidden layer, and then the output of this first hidden layer will be an input for your next layer. So it goes on like that. And if I want to add another hidden layer, let me call it second hidden layer. I follow the same steps. Model.add, we add a dense layer. Let's use 512 neurons, and then we specify our activation by calling the model.add method and then pass activation, and we'll use sigmoid for activation. So the output of our second hidden layer will be an input for your next layer. So this is a multi-layer perceptron with two hidden layers. We have our input, output, and any layers in between will be your hidden layers one or more hidden layers. And again, for your output layer, we specified softmax. We use softmax because we want to convert our evidence into probability. And we do that by using softmax, okay? As it gives us a list of values between 0 and 1, and that can add up to 1. Okay, that's why we always use softmax as our final output layer. And for our output layer, we specify number of classes, and it will automatically take the output from your previous layer. After that, we call our compile method, and this is used to configure the learning process. And as we mentioned before, this compile method takes 3 parameters: loss, optimizer, and metrics. And optimizer is what we use for learning. This is the learning method, and we use this optimizer to minimize the loss. And for sequential models, we want our metrics to be accurate. So most of the steps are the same as in our previous lecture. We just added a couple more hidden layers. So let me run the cell, and then we'll call the fit method to train our model with our training datasets. And we pass a few more parameters: batch size, number of epochs. Our batch size is 256, number of epochs is 10, verbose, and we'll be validating the X test and Y test. So let's run the cell. So the first epoch is running, and this might take a few seconds. So about 4 seconds for the first epoch. And here you see the loss, 6985, and accuracy. So as we go through successive runs, we are trying to minimize the loss here. Okay, that's what the optimizer tries to do. Okay, let's give it some time. So we have 2 more epochs to run. Okay, it has finished running. What we'll do next is call the evaluate method to evaluate our accuracy. Let's do that. So model.evaluate, and we'll pass our X test and Y test datasets, and we'll set the verbose to be equal to 0, and let's save this in a variable called score, and let's print out our score. Okay, score will index 0. So this is the same thing that we did in our previous lecture. Score. Okay, let's run this. So here we have, let me change this to accuracy instead of score. Accuracy, run it again. Okay, here we have an accuracy of 89.7%. If you remember in our previous lecture, we had an accuracy of about 94%, right? But here we have accuracy of almost 90%. Why do you think the accuracy is lower? Even if we put more hidden layers, we increased the number of epochs and we added 2 more hidden layers. But despite all that, we had a lower accuracy. So one challenge with neural networks is a condition known as overfitting. That's one challenge we have in neural networks. And as you see here, our model has 784 inputs, right? And it gets connected to 512 neurons in your next layer. And each of these 512 neurons get connected to another 512 neurons in your next layer. And those finally get connected to your output layer. So at the end, you'll have so many parameters in your network, right? And that condition is known as overfitting. Again, you have 784 inputs and 512 neurons in your input layer, and you multiply that, you get your weight, and that gets connected to your next layer, and your next layer has 512 neurons, and then multiply that by the weight from your previous input, and that gets connected to your next layer. So the output of your first hidden layer will be the input for your next layer, And when you multiply that by the number of neurons, you get the weight, and that connection goes on and on. So you have so many parameters in the network, right? At least 1,000,000. When you multiply the weight, and then that gets transferred to your next layer and acts as an input for your next layer, and you multiply that by your neurons. And so the weight keeps adding and adding, and you'll have so many parameters. And this leads to a condition known as overfitting. And that takes us to our next lecture. We'll look at what is known as regularization. And this is a technique we use to reduce overfitting. We'll look at one method of regularization known as dropout. So keep in mind there is a condition known as overfitting, which is a challenge in neural networks. So in this lecture, we added 2 hidden layers, right? And I wanted to show you that. As an exercise for you, what you can do is only add 1 hidden layer. So remove the second hidden layer and work with only 1 hidden layer, so that you'll have an input layer, your hidden layer, and an output layer. And change these parameters, batch size to maybe 128, or you can keep it the same, and change the number of epochs to 5 or 15, and compare the result you get with what we did in this lecture. Okay, thank you everyone, and see you at the next lecture.